Okay, so we just talked about the requirements for using Bernoulli's equation, and we also went over the derivation of Bernoulli's equation. We found out that you need to have steady flow, no viscous forces, flow along a streamline, and our density has to be a constant. And we also talked about how steady flow is not tremendously common, and it's almost impossible to get no viscous forces. There's lots of situations where we can have close to no viscous forces, but no viscous forces is nearly impossible. And so despite the fact that we can't actually exactly meet the assumptions we need to use this equation, it's quite useful in a lot of situations. So we're gonna look at one situation where we can try to use this equation, and it's in draining a pool. So we have a pool sitting on a slope. We're gonna put a hose in it, use the hose as a siphon, um, and ignoring viscous effects. How long will it take the pool to drain? Well, remember, every time you're given a question, you should ask yourself, what model do I need to use to answer this question? And so when we want to know how long it takes to drain, we're talking about flow rates and heights, because we're given heights of the pool. And so we can use our velocity from Bernoulli's to calculate flow rates, and we have heights in Bernoulli's. So the tool that we're going to use to solve this problem is Bernoulli's equation. Pressure divided by density plus velocity squared over 2 plus gz is equal to a constant. Now in practice, the fact that this is equal to a constant everywhere along a streamline means that we can compare 2 points along a streamline, and we know that at those 2 points, this summation has to be equal. Which means that every time you use Bernoulli's, essentially what you're doing is you're drawing a streamline, and you're going to analyze 2 different points on that streamline. So I'm going to pick a streamline. I'm going to start here, and I'm going to pick a streamline here at the exit. So I'm picking a surface, and I'm coming down, and I'm drawing my streamline. Here. Now, over and over again, people choose not to draw streamlines on the exam, and over again, people miss problems, and it's frustrating. Trust me, if you draw a streamline, it makes your life easier, because it makes things very clear. So you're going to label this as point 1, this is point 2, and now what we're going to do is we're going to apply Bernoulli's between these 2 points. Okay? So how we chose these 2 points, by the way, is very important. Point 1 we know is a surface, so we know the pressure at a surface because the pressure is equal to atmospheric pressure, and we know the height. And we chose a point just outside of our hose because we know the pressure there as well. We know that a free jet of water that's just leaving a hose has a pressure that's equal to atmospheric pressure. Inside the hose, because of a whole bunch of reasons, the pressure is not going to be equal to atmospheric pressure. So let's write out our equation here. So we have equation 1 to equation 2, and remember, we're labeling our equations to help the graders and help our future coworkers. And we're going to use our 2 points here. So we have P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. Great. Fantastic part is that P1 and P2 are equal, so we can cancel out our pressures here. One thing that's really important is that our areas, we know that as the water leaves this tube, this surface is going down, right? And we'll cover this in much more detail later, but one of the equations we're going to use is called conservation of mass for incompressible fluids. But what it tells us is that V1A1 is equal to V2A2, which kind of makes sense, right? If we know that the mass that is leaving here has to come out of here, and the area of this is much smaller, the velocity has to be much greater. So what's great is, actually we'll call that equation 3, sorry, this is equation 3. We know that from equation 3, because we're going to assume A2 is much, much smaller than A1. We're going to call that our first assumption. We can, from equation 3, we can tell that V2 is much, much greater than V1. Okay? And if we're going to square something that's much, much smaller than something else, we can essentially neglect it. So we're going to neglect this due to assumption A. Great. So now we have GZ1, V2 squared 2, GZ2. We know Z1, we know Z2. We don't know V2, but we can solve for it. So, let's plug in our numbers here. We get that V2 squared over 2 is equal to G times Z1 minus Z2. If we plug in our numbers, we see that this is equal to, cancel that up, put the 2 over here, 2 times 9.8 meters per second squared times, what are our different heights? Y1 is 1 meter, Y2 is negative 2 meters, so we have 1 meter plus 2 meters, and ends up being square rooted. So our V2 is equal to 7.6 meters per second. Now, for the record, we could also plug in this equation into here because we have a relationship between V1 and V2. So if we hadn't canceled out V1, we would have had 2 unknowns. So we would need a second equation in order to solve for our V2. And that second equation would have been V1A1 is equal to V2A2, because we can say that V1 is equal to A2 over A1 V2, and we can say that V1 is equal to, we know our diameter, relative diameters of our system here. We got 0.01 meters squared times pi over 10 meters squared times pi. Those cancel out, but V2, and actually here now you should be able to see, we should do that. We should be able to see why our assumption is actually quite good. We have 0.01 squared, which is 0.0001, and we have 10 squared, which is 100. So V1 is smaller than V2 by a factor of 10 to the 5th or so. Much, much smaller. So this is actually quite a good assumption. And we could plug that into this equation and do a lot of algebra, but instead we're going to cancel it out. So if our velocity is equal to 7.6 meters per second, and we want to figure out how long it's going to take our tub to drain, we're going to use, again, equation 3 along with this. So we're going to pull this down here. We know that V1 is equal to, so let's actually label this for our graders. I got carried away when I was talking about stuff. This is equation 3 to equation, this is 2 to equation 4. We'll call this equation 3 to equation 5, and equation 5 to 6. We know that V1 is equal to essentially 0.01 meters squared over 10 meters squared times 7.6 meters per second, and we can solve and find out that V1 is equal to 7.8 times 10 to the 6th meters per second. So the surface of our pool is falling at a rate of 7.8 microns per second. So after about 12 to 15 seconds, it's going to fall the width of your hair, roughly. It's always good to have stuff like that in your head, right? That relates lengths to things that you can easily intuitively understand. So about 100 microns is about the width of your hair. So this is going to fall in about 15 seconds, about the width of your hair. And if we want to solve for the time, we're going to take 6 to 7, and we're going to say t is equal to distance divided by velocity. Actually, that's an equation all by itself. That's 7. And then 7 to 8, let's plug in all the values. We find that t is equal to, the height of the pool is 1 meter. So we have 1 meter divided by the velocity, which is 7.8 times 10 to the negative 6 meters per second. And that gives us a time is equal to 36.2 hours. Now, my question to you is this exactly the time that this pool is going to drain, right? Because remember, what models do is they predict the behavior, well, for us, of physical systems. So we're trying to predict how long it will take this pool to drain, and what model we've used is Bernoulli's, and we've made a few assumptions, but in addition to Bernoulli's, but those assumptions were pretty good. And the question is if basically, this is a good way to put it, if you had to place a bet, would it take longer or shorter amount of time for the pool to drain? All right, I'm going to give you a chance. Pause the video, debate it with your friends, call in a favor to other people, but tell me whether or not you think it would take longer or shorter amount of time. All right, hopefully you paused the video and then restarted it because you made a guess and you circled it on your own. The answer is it would take a longer amount of time. Okay? Now, let's talk a little bit briefly about what makes a model conservative or not. So, generally speaking, when you're draining a pool, you want the pool to drain faster. And so a conservative model is a model that has errors that you know about. You don't know exactly how big those errors are, but you know it has errors, and those errors will tend to make it so that the model's prediction is worse than the actual behavior of the system, if that makes sense. So in this case, our model's prediction is less than what the actual system would actually do, and so our model is not conservative. It's not a conservative model. All right, so why would it take longer? Why is this not a conservative model? Why would it take longer than we would expect for this? Why would it take longer than this predicts for the pool to drain? And the reason is that Bernoulli's neglects viscous effects. So remember, the pipe is small, and viscous effects scale proportional to the viscosity times ratios of velocity to length, right? So if we have a velocity in our tube moving in this direction, and perpendicular to that velocity we have a short length like we do here. The diameter of this tube is quite small. It's 1 centimeter. It's 1 centimeter. That is a small tube, huh? So we're going to actually have fairly significant viscous effects in our tube that are going to slow this down. The other thing we did not do is we did not analyze this as as a dynamic system. We assumed that the flow rate was going to be the same no matter what the height of this pool was, but it's not. Our velocity is actually a function of our height. And so if we wanted to do this correctly, what we would do is we would solve for velocity as a function of height, like we did here. And then we would do some kind of integration along the height to figure out the this velocity here, v2. Actually, we would solve for v1. Sorry, we would solve for v1, which is dh dt, and we would end up dy1 dt, and we would integrate that in order to solve along here in order to solve for the actual time it would take. That's actually a really good problem. We should do that sometime. Okay, so for two reasons, this is a lot slower. One, Bernoulli's neglects viscous effects, and two, we did not take into account the dynamic nature of the problem. Cool. So let's now take a look at our semester-long design problem and how can we use Bernoulli's to tackle our space tower. So just a reminder, our semester-long design problem is we have a space tower. Let's call this Lake Erie here. This is Lake Erie. And what we're trying to do is we're trying to put pumps on a space tower, and then we're going to shoot jets of water down to produce thrust in order to raise something. At this point, we're just shooting for a person as high as we can towards space to reduce the cost of getting an object into space. Lots of people are doing this with planes, right? The guy, I forget where he won his money, but somebody has created the largest plane ever made, and what it is two 747s that they literally bolted together, and they're going to try to fly rockets up as close to space as they can and then launch them. Saving some money on rocket fuel, and also making the rockets a little bit more reusable, I believe. So what's interesting about this is we can apply Bernoulli's a little bit to figure out perhaps what is the maximum pipe length from pump to jet, assuming again that we have a single pump down here. So here's our single pump. You know, perhaps one of your coworkers is again like, yeah, I understand, because remember in hydrostatics we said that we couldn't get up to 60 kilometers like we wanted to with a single pump. But this guy is like, yeah, you know what? Maybe we can't get to 60 kilometers, but maybe we can get to 20 kilometers. And so what we're going to do is we're going to solve for the maximum pipe length from this pump to the jet. And remember that the mode of failure that we're worried about here is the pipe actually bursting, because all of this water in this tube is going to create a lot of pressure here down at the bottom. Okay, so our design is going to fail through bursting of the pipe, and we're going to apply Bernoulli's and see if we can figure out exactly how high our system can get. So the fun part is we're going to choose a V exit of 33 meters per second. In reality, that is not nearly enough to produce thrust necessary to get this up high enough. We don't know how to calculate the thrust yet, so we're not going to worry about it. We're just going to assume a velocity exit at 33 meters per second. If you listen to the fluid statics video where we first talked about this, we're going to see that you need supersonic jets coming out of here, which is just going to be just incredible, just a huge roar and lots of clouds and stuff. So, but here, 33 meters per second is our exit. Our pipe diameter is 60 centimeters. The thickness of our tube is 3 millimeters, and the radius of our tube, like I said, our diameter is 60 centimeters, but our radius is 30 centimeters. And the radius of our nozzle is 2 centimeters. Great. So with all this information now, we can start to solve this problem. So we know that we're worried about the pipe bursting, so we're worried about the pressure within the pipe, and we have velocities, and so we're going to use Bernoulli's as a model to try to calculate pressures. So let's write out our Bernoulli's equation. Equation 1, we have P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. And remember, we have to assume some stuff in order to get this to work. So let's write down our assumptions. One, we're going to have to assume inviscid flow. And remember, we're writing this down so that our future coworkers know we had to assume inviscid flow and that's a terrible assumption. But we have to, because right now the only tool we have to tackle this problem is Bernoulli's. So we have inviscid flow, density is equal to a constant. That's a pretty good assumption, right? And we assume that it's also steady. Steady is not a bad assumption. We're doing the same things over and over again. So, yeah, let's draw our streamline now. So remember, every time you use Bernoulli's, you have to draw a streamline. And so we're going to draw our streamline from, and let's redraw this system, make it a little bit more clear. We have a pump, we have a tube coming up, and then down, pointing down. And we're going to draw our streamline from just outside the pump, up, out to here. So here we have 0.2, here we have 0.1. Great. Let's solve this. So 0.2. Let's do some simplification if we can. We're going to assume gauge pressure, so let's make that assumption D. Gauge pressure. And if we have gauge pressure, then P2 is going to be equal to 0 due to assumption D. Great. Let's draw in a coordinate system because we're measuring heights. Let's make our coordinate system 0 at 0.1 because we can. X, Y. So if point Z1 is at 0, this becomes 0. That's great. And let's talk about the things we know and that we don't know. So we know V2 because we're given it 33 meters per second. We know V1 eventually. We don't know it quite yet, but we're pretty sure we can get it because we have continuity. We have conservation of mass on our side, and we know we don't know Z2. And we don't know P1 yet, actually. Let's put a question mark there because we're going to have to solve for it. So we have P1 we don't know. We don't know V1 yet. We're given V2, but we don't know V1. And we don't know Z2. But Z2 is ultimately what we're solving for. So we're going to try to get equations now. We have 3 unknowns. We need 2 more equations. So let's get 2 more equations out of this. Equation 2 is going to be that V1 A1 is equal to V2 A2. And we know A1 and A2 because we know the relative diameters of the nozzle and the tube. So we can solve for V1. So 2 to 3 gives us that V1 is equal to 33 meters per second times, and we'll do the ratio of the areas here. So 0.02 meters squared over 0.3 meters squared gives us a V1 that's equal to 0.147 meters per second. Cool. Now we need one more equation to tell us our P1. Well, we know that the failure that we're worried about is pipe bursting. So if we want to know the highest height we can go, we're going to try to figure out the height at which the pipe bursts, because any higher than that, obviously it fails, and slightly lower than that, it works. So if we do a cross section of our pipe here, a little cross section of our pipe, we can see that if we draw our pipe, and I think you guys have done bursting pipes in solids if you've taken solids. Perhaps you haven't yet. But we have a certain thickness of our pipe T, which has a radius which we know. And inside of this pipe, if we draw a volume like this, we can see that a volume all the way around it. If we draw a volume all the way around it, what we see is that we have a pressure force from inside of the water that's pushing in this direction on the control volume. That's what we have. It's called a control volume. But we'll go into much more depth about that in chapter 5. And then also acting on this cutaway is a tension within the pipe that's pulling in this direction. And that's it. That's the only things that are acting horizontally on this pipe are pressure from the inside pushing the thing out, and then tension within the pipe holding it together. So again, we should go straight to our equation 4. Sum of our forces is equal to mass times acceleration. We'll go to the basic equation of mechanical and aerospace engineering. 4 to 5, if we draw x and y, we have to draw our coordinate system here. 4 to 5 gives us sum of our forces in the x direction is equal to, and if we add these up, we see that this pressure here is going to give a pressure inside times our area, and what our area is our diameter, or 2 times our radius. 2 times our radius is our pressure, times some unit depth into the page. So we're going to just put a 1 there. And then our our tension within our tube is going to be equal to our stress within our tube, sigma, times twice the thickness of the tube, times some unit depth into the page. So if we add these up, we see that the pressure is negative, so negative P times 2R minus, plus our sigma times 2T. Great. So we know our thickness of our pipe. We know our yield strength of our pipe. We know our radius of our pipe. So we know everything in this equation except for our pressure, and we can solve for it because this is stationary, so it's equal to 0. So we got 5 to 6. We can say that pressure is equal to, when we solve for everything, sigma yield times the thickness divided by the radius. And if we plug everything in, 6 to 7, we see that pressure is equal to 3.5 times 10 to the 8th megapascals times our thickness, which is 0.3 centimeters, divided by 30 centimeters. And that gives us a pressure which is equal to 350 kilopascals. You'll note, hopefully, right, if you're trying to figure out how large pressures are, that's only about 3 atmospheres. So a 30 centimeter diameter tube that is 3 millimeters thick is really only rated to about 3 atmospheres of pressure, which is not much, right? So what could we do to make this pipe hold more pressure? Well, we can decrease the diameter, make this smaller, or increase the thickness. And that's really the only options that we have. Unfortunately, we don't want to do either one. Increasing the thickness increases the weight of the tower, and decreasing the diameter of the tube increases the viscous losses within the tube, right? Because remember, viscous losses are always scale with the velocity over the thickness, so or over the length, perpendicular to that velocity. So we have fluid coming up. Let's draw a little arrow coming up through this tube. So the distance perpendicular to that velocity, this distance, as it gets smaller, our viscous forces get larger and our viscous losses get larger. And eventually we'll have to pay for that. Now we don't know how to calculate that, but eventually we will have to pay for that. So, but for now, let's assume that we're using this tube. Perhaps it's a tube we have laying around. Who knows? But we've used this tube with a 3 millimeter wall thickness and a 30 centimeter diameter. And it gives us a pressure of 350 kilopascals. So now we can plug in this pressure up here. We know that pressure. We have our V1, and we can now solve for Z2. So if we plug everything in, solve for this, we get 1 to, what equation are we on now? 1 to 8. We're on equation 8 now. We can solve for Z, and we find out that Z is equal to P1 over rho G plus 1/2 V1 squared over G minus 1/2 V2 squared over G. And if we plug everything in, we see that this is equal to 350,000 pascals divided by 1,000 kilogram per meter cubed times 9.8 meters per second, plus 1 over 2 times 9.8 meters per second squared times 0.147 meters per second squared minus 33 meters per second squared. So you can see, by the way, small velocities squared become almost completely negligible. And if we plug in all of our numbers, we see that our Z is equal to 302 meters. So your coworker that was just trying to wing it is completely wrong, which is why we don't wing stuff in engineering. We calculate stuff. That's why you spend 4 years learning how to calculate stuff and use numbers to solve problems. So how could we increase this distance Z? Well, like we talked about, we can increase the the pressure, or sorry, we can increase the thickness of the tube so that we can get more pressure at the beginning. We could decrease our velocity at our exit, but that would actually make it so that we get less thrust, which we don't want to do. So there's not a whole lot to do. We will see later that you can use staged pumps. We don't have to have a single pump at the bottom. So we might want to use staged pumps. We might want to put pumps right next to nozzles so that the pump exits directly into the nozzle. There's lots of stuff we can do. But with this basic kind of configuration of a pump at the bottom, you can't get very high. So is this a conservative model? Remember, a conservative model predicts results that are worse than reality. So worse implies good and bad, right? So in this case, a good result is a taller result. So the question you're asking yourself is reality going to be, can we build a tower in reality that's taller than what the model predicts? Or will it fail at shorter heights than what the model predicts? A conservative model will fail at a shorter height than reality, right? If we built this thing and then tested it. So, will this thing fail? Will reality fail at a shorter or longer height than what this model predicts? And I'm going to let you pause this and answer that question. Debate it. Call people. All right. So, is this a conservative model? And the answer is no. In fact, this the tower will likely fail at a shorter height than what this model predicts. And the reason is this neglects viscous and dynamic forces. The big one here is viscous forces. Both can be large here, but viscous forces are going to cause a large pressure drop to occur between 1 and 2. So in order to maintain that velocity at 2, you need even more pressure to overcome viscous losses at 1, which means we're going to have even higher pressure, which means we need even shorter tube. So this is not a conservative model because it predicts failure at a height that is higher than reality is likely to fail at. Another way to think of a conservative model is if you predicted this height and you were standing on top of this thing and you had them build it exactly to this specifications due to this model, would you be happy or sad? And the answer is you'd be sad because you'd want it to be shorter than what this model predicts. Otherwise, you're probably going to sit and fall. All right, that's our example problem and our semester-long design problem. The next segment is just going to be a whole bunch of practice for Bernoulli's equation.